Hi. Well, I'm going to tell you a story that will be very unpopular in this university. I understand that in this university you should do research today and get money for it 3 weeks from now. Okay? What I want to describe to you is work which has been done for curiosity. And all of a sudden made a lot of money 50 years later or 100 years later. And that's what we should do today. We should do basic research so that there will be some money coming in for the generation that works 50 years from now. Okay, that's a message I want to convey to you. And what I will use as an example is my own technique, nuclear magnetic resonance, and I will show to you how this physics. Who knows what NMR is? Well, do you know? Yes? Surprise. And I will show that it's used to study intact human bodies and to study molecules. So what we want to get are structures. Since you are so much into money, here exceptionally I worked with a company on a drug development project. This drug is cyclosporine A. It has sold for more than $1.5 billion ever since 1984. Okay, it's a good drug because it's used when you make a heart transplant or any organ transplant. And once a patient has had a transplant, he has to eat the drug for the rest of his life. And thanks to the drug, he may live for 30 years. That's a good drug. A bad drug is for flu, which lasts for 3 days, and then you don't eat it anymore. Or this other structure that has part of a structure protein, part of a flexible tail, and when this flexible tail does something wrong, then you have mad cow disease, or Creutzfeldt-Jakob disease in humans. Or then you can use the same physical principle to get images of the body in medical diagnosis. Who has been in an MRI among you? Who has had MRIs taken? Nobody? Are there MRIs in Russia?
Yes.
There are?
Yes.
How many? 2?
No, quite a lot.
I'm surprised that no one.
We have a lot in MFTI actually. We have some in MFTI.
Okay. So, the first basic science in this is summarized in a book by a Russian scientist, Amragan, who wrote this book about nuclear magnetism in 1961. That's a sort of 6 it is. You see there are my handwritten notices. The text is from Amragan. It's all of this, more of this in my handwriting, more of this, more of this. That's a sort of basic research. And here you don't see so many at the other end of the line. Well, then we do our own more equations. That's basic research that you do. Easier to exercise your brains or to challenge yourself with doing something difficult. All right. Having done this, you can start to blow hot air and talk about results. So there have been 6 Nobel Prizes in NMR. The first 2 in 1952 for the observation of the nuclear magnetic resonance phenomenon. So what this is, I describe it for a nuclear spin with spin quantum number 1/2. Spin quantum number 1/2 gives rise to two eigenstates, with plus 1/2, minus 1/2. In the absence of a magnetic field, the two states are degenerate. You cannot distinguish them. When you apply a magnetic field, you get the so-called Zeeman effect. That's a physicist who got the Nobel Prize. He doesn't count for the NMR. He got the Nobel Prize in 1902 for having discovered the splitting between the two energy levels. When you apply a magnetic field, he saw this in optical spectrum. And then the next step is the real NMR, which means that two guys in 1946 were able to observe transitions between these two levels, which is not trivial because it's a very small energy, and the population of two energy levels is almost identical, so there is no sensitivity and so on and so forth. But anyway, this was one of the two, Felix Bloch. This is Ed Purcell. So these two guys invented NMR in 1946. By the way, in 1945, a Russian scientist, I think his name is Savitsky, discovered EPR, the same phenomenon with electrons. It was, he never got a Nobel Prize. I think, I don't honestly know why, but it is a fact that ESR was discovered here in Russia 1 year before NMR. It could be that it was only published in Russian and nobody noticed it until 20 years later. What's going on? Oh, okay. Now you study difficult things. You study water. Okay? Okay, water has a simple structure which you probably all know from high school. H, and O. And when you now make an NMR experiment, you only see the hydrogen atoms. The oxygen you don't see. And then you get this one line. It's pretty boring. But then you can have a good idea. And the good idea here was to consider that the energy splitting between the two eigenstates depends on the strength of the magnetic field. So if you apply a magnetic field again across a macroscopic object and you change the strength of the magnetic field, then you can distinguish between identical compounds in different positions of the macroscopic object. Do you think? You see, this is what I'm talking about. If I have to go back. If I have just the field B naught, and then B plus delta B and B plus 2 delta B, and if I add small amounts of field strength, then this splitting becomes bigger. Okay? That means the frequency of the radiation that you need to induce transitions between the two quantum states changes. It becomes bigger when you go from here to here to here. And therefore, you can distinguish between the line of the water on this side of the head and of that side of the head. See, you have then three lines. The one outside the head, the one at the right ear, and the one at the left ear. Okay? Now you are able to see the water here, and you see the water here. And then you do the same experiment and apply the field gradient from front to back, and then from top down, in 3 dimensions. And then you develop mathematical tools that can calculate a 3-dimensional image from these measurements. And all that is always observed with water. This happens to be my need, which I needed sometimes. And the guys who had this idea about using these field gradients were Paul Lauterbur and Peter Mansfield, they got the Medicine Nobel Prize in 2003. And here you see Peter Mansfield standing next to him on the MRI. And this magnet where you will put the patient in and expose him or her to the magnetic field and do his experiments. I was also very early on involved in this, and we studied babies in the children's hospital. The newborn babies, we had to check everything while they were in the magnet, because they might die while they are in the magnet, because they are usually very sick when we were allowed to study them. And to make it more fun, we built a little fairy house around the magnet here is the baby. And then, unfortunately, you see sad pictures like this, where you have a huge hematoma here in this road of the brain because of mechanical trauma during birth of this child, which we studied was about 2 weeks old. Okay, so you see, we have a great breakthrough in 1946 when 2 physicists discovered NMR. Then nothing much happened in this direction for 30 years. And then came the next idea, which was to use these field gradients and develop mathematical tools to make images. And then it took another roughly 20 years to make this into a viable method for medical diagnosis and the materials research. See, there is no, today MRI is a $1 billion-a-year business, created thousands and thousands of high-tech jobs because each instrument requires 2 or 3 people to operate it. In China, for example, they are understaffed with MRIs. One can estimate that they need at least 5,000 MRIs if they want to come up to the level where we are in Western Europe and in the USA. And so there is feverish activity. About 10 startups in China who try to get into the market of MRIs to get a piece of those 5,000 units that they estimate will be sold in China. Then all of a sudden, there's a lot of money, a lot of people who benefit, but it is thanks to the fact that basic research without any consideration of possible rapid returns has been done. A bit similar, the development of using the same physics phenomenon in structural biology or in chemistry, by the way. Here, the problem to be solved needed another idea, not field gradients, because now we are not talking about the head with 30 centimeters across, now we are talking about molecules which are 10 to the minus 8 centimeters or so in dimension. So we have to do something different. And things are different from the start because we don't have just one kind of atoms, for example hydrogen or carbons, but we have many in protein structure. And each atom gives a separate line in the NMR spectrum. That's what you get. And here, these are just a few nicely resolved lines. But here is the bulk. It is more difficult than an NMR spectrum. Here you have about 1,000 lines that overlap, and we can't do anything. So we have to invent 2-dimensional NMR. See, now you go into 2 dimensions. First, the 2-dimensional time space, and then Fourier transform into a two-dimensional frequency space. Then you have two orthogonal frequency axes, and instead of having an S on a single frequency axis, which is here on the diagonal, you get the light spread out in two dimensions. And this can, that's brand names of the first set of such experiments which we used to solve the initial protein structures, which goes in also sexy and foxy. And just to give you an impression of what is done, what the basic idea is, I mean, similarly qualitative as with the imaging. So, when you look at the watch, the time runs continuously, okay? And now you take a spin, say this quantum mechanical unit, and you hit it with some physical device. I mean, it could be, I could hit like this, okay? My arm, that goes here, and then I leave it for a little while. And then I hit it the second time. But while between the two hits, the arm moves. And so it will have an impact if I hit, and then I wait for 1 second, and then I hit it here. If I wait for 5 seconds, the arm must move that much, I hit it here. And then the effect is different, of course, whether I hit here or here, with the second perturbation. That's the second time axis. See? Then I do this 100 times, and each time I wait for a different time here, T1. And if I have 200 time points, then I have my second time axis. That's how we create two-dimensional time space. And today, we use every day routinely 4- and 5-dimensional experiments, and sometimes 7-dimensional experiments. We just add another perturbation, another one. We just need some additional technical knowledge. And then from the two-dimensional data matrix, you go to the two-dimensional frequency matrix, like two-dimensional Fourier transformation, and my colleague Richard Ernst got the Nobel Prize in 1991 for this. And then when you plot such a 2D spectrum in a suitable way, you get to see just how much information there is. Then again, similar to MRI, magnetic resonance imaging, new algorithms had to be written and programmed. This was based on distance geometry principles, and then you get the structure. Now, you see, all other methods than NMR who can determine such a structure, fix the molecules in a crystal lattice, freeze it, so that it's fixed, and then you can make an image. And so, when I started out with this, everybody told me you are losing your time because this thing moves all the time, you can never make an image because it moves so fast with a typical time of 10 to the minus 9 seconds. That means after 10 to the minus 9 seconds it has changed its orientation so much that you have a completely sphered image. So we cannot make an image as we do with the human head. But why the molecule moves, the distances between pairs of atoms in the interior are maintained. See, and the thing is folded, and then you rotate the molecule to translate, but the distances between the atoms in the interior stays the same. And that had to be realized, and that's how you can do it. Yeah, then you get the Nobel Prize for such. That's all right. So we have now three key things in the spectroscopy field. I mean, you have to observe NMR, that gives this physics Nobel Prize for 2. You have to have the idea of applying field gradients across macroscopic objects. Another prize for 2 in medicine. And then you had to introduce two-dimensional NMR. I gave two separate Nobel Prizes for Einstein myself. Nobody knows why we didn't get it together, but that doesn't matter. Because we published 40 papers and then we got the Nobel Prizes every distance of 10 years. Now, there is one thing left. That is to ask why can we do this? What is the basis? You see, it was just done, and it wasn't particularly, it wouldn't be particularly clear just from the NMR experience why it works. And that goes much further back to scientists who did basic research without any interest in whatsoever. The first one was Mr. Brown in England in the 19th century sometime, I think 1835 or so. He took a microscope and looked at small particles that he had suspended in oil. And then he noticed to his surprise that these particles were moving around in the oil. Like this. Okay? Translational motions. And he had small particles, they would change direction at high frequency. When he had large particles, they would change direction at low frequency. He didn't understand why, he just described it. This is the famous Brownian motion. It took about 70 years until another guy, this one, got into the picture. And he analyzed the situation of these moving particles in two publications in 1905. One publication dealt with this movement, the other rotate. And Einstein had the right idea of what's happening. The smaller solvent molecules around these balls all move because we are at 300 degrees Kelvin. That's high temperature. So you have a lot of thermal energy. They move and they hit the surface of the particles, in our case the molecules. And because this is slightly asymmetric, you get stochastic reactions of the suspended particle to this compartment. This treatment was also the start of serious statistical mechanics. The translational movement paper was published in May 1905, the one on rotational motions in December 1905. And it led to the so-called Stokes-Einstein relation, which simply says that the molecular size determines the so-called correlation time for rotational motions, and this affects all the important NMR parameters. If we didn't understand properly how the relation is with the correlation time, which is determined by the Brownian motion, we would not have been able to use the NOVs to nuclear overhauser effects to measure the distances inside the molecules, which enabled us to get three-dimensional structures. And we would also not understand why we see pictures, sharp pictures of human bodies. So it doesn't make sense at first glance. You look at hydrogen resonances, and hydrogen atoms are everywhere. They are in our flesh, they are in our in the skin, the hair, everywhere. But all we see is a sharp line when we look at the human body. And this also is rapidly explained by the theory of Einstein. Namely, the voltage is very small, it rotates very rapidly, it rotates rapidly inside our body fluids, whereas all larger particles inside our body are essentially immobilized. And because of that, the correlation time is such that the transverse relaxation time becomes so short that we don't even get a vacuum. So, and of course, knowing exactly what is happening, it then enables one to refine the imaging techniques. So we now have T1 weighted MRIs, we have T2 weighted MRIs, we have T1 row weighted MRIs, and so forth. And it all depends on, it all derives from theoretical work that was published 109 years ago, without any vision by Einstein of what this would be good for. See, there was no NMR for 50 years after he did this work. Then, when we go into a bit more involved questions, we can analyze the evolution of the NMR phenomenon in terms of single transition basis operators. That leads to prosing, and thanks to prosing, we can also not only measure the resonance of water in intact human bodies, but work with small-sized proteins, but also we can work with particles that are as big as 1 million. We can work with membrane proteins that we isolate from the membranes in mice cells or similar carriers. And again, here the application that's currently just started here in your university by a colleague of mine. He will study crystal structures of GPCRs, G-protein receptors, and by NMR we will try to explain how signals can be dynamically transmitted across the membrane through these protein molecules. Again, it all depends on having done serious basic research decades ago, 100 years ago in one case. Then one day there comes a big breakthrough for the engineers and for the bankers. Thank you. Your professors will be very unhappy. They want you to get some money next week for your work. I just hope that you next day. Yes?
If you want to check.
What to do?
Yeah, I wanted to ask you a question, only for ignorance, but are there any teratogenic or harmful effects towards humans shown by NMR?
No, the question, you meant when one does MRI. At least 800 pictures taken of me.
Yeah, I mean,
I'm more or less intact.
sure, but you were adult while you've been taking those pictures, right? But should it harm
The baby?
fetuses? Yeah.
Fetuses? Why should it harm fetuses?
No idea. Because the development of fetus includes the certain determinants, right? So distribution of factors.
No, look, I mean, we agree that making images and using such technology as a non-invasive method of diagnosis in human medicine is useful. Right. Now you have two principal methods to look at joints and knees or ankles or stuff. And one is X-ray, tomography, and the other is MRI. X-ray tomography uses the radiomagnetic field that has energy which is about 10 to the 30 times higher than the one that we use for MRI. 10 to the 30. Okay? Now if you radiate the fetus with X-rays, then there is certain danger that will use radiation. I mean, you would not normally subjective regulatory in that area to exist. We try to prevent it. The energy that you transmit to a body with the MRI is very, very there has been talk about the possibility that interaction with the radio frequency would interfere with the elevation, for example, of the heartbeat, that it could lead to how do you call this, fibrillization, to uncontrolled heart movements. There have been, to the best of my knowledge, there has been no incident documented. So don't worry about it. And you do not usually use MRI to look at it. You have even more conservative. You also need to explain.
Question. Today it's not possible to solve the structure of the whole big protein. For example, GPCR is rather big, and it's possible to solve the structure only with X-ray.
Who told you so?
No, I've heard that. Yes, in most cases, in NMR, use in NMR research are used only parts of big receptors. For example, I know that
we always work with intact GPCRs. Okay, we never take pieces of it. Yes. We do NMR with GPCRs. The only reason that we didn't solve the structure of a GPCR is that it would be much more expensive. We could do it, there's no doubt. But it would be more expensive than doing it by crystallography. And therefore, in this case, we let crystallography do the structures, and we then get information on the dynamics and on conformational equilibria. But we always work with the functional, complete GPCR reconstituted either in nanodiscs or in dissects.
I guess the question was by providing more structures are much smaller than the average X-ray structure.
But they are not small.
No,
if you make a structure of a given protein, it will have the same size, independent of whether you do it with NMR or with crystallography. Okay? Well, I'm just kidding now. It's semantics. But why do we mostly work with smallish proteins? Because these are the proteins that are more difficult to do by crystallography. That's the main reason, because in smaller proteins you have a larger percentage of surface exposed area compared to interior contacts. And therefore, that has two consequences. One is that statistically it is more likely that the smallest protein cannot be crystallized, so that it diffracts. It's a fact. And the second point is that because you have larger surface area compared to the mass of the protein, you have bigger differences between the crystal structure and the solution structure than for larger proteins, whereas the interior is usually essentially identical in solution and in the crystal. And then, of course, it's easier to do smallish protein structures. You see, through solved protein structure with 150 residues and molecular weight 20,000, we do this like that in a week. Now, completely automated. Just as crystallography does it in half a day, once AF crystal. The difficulty is to get the crystals or to get the good solution of the isotope-laden protein. This is often a big barrier. As soon as you cannot express the protein in E. coli, you are in trouble. If you try to do a structure by NMR, when the protein is larger than about 200 residues. But they have the same size, independent of which method you use in studies. All right. That's it.
We have a tradition here to design the walls over there. You're sitting if you don't mind, could you please do it for us? I mean, thank you very much.
I don't have a pen.
Well,